So welcome to this quantum information and coherence talk, QuiC Talk. So today we have Swati Chaudhary as our speaker. So Swati did her BSc from Delhi University in 2013. Her MSc is from IIT Kanpur. So yeah, she is one of our own. She finished that in 2015. Then she finished her PhD from Caltech in 2021, and she has been a postdoc jointly at University of Texas Austin at Northeastern University in the US. And today she is talking about phonons with angular momentum, magnetic properties and application. So yeah, Swati, welcome to IIT Kanpur, and we are looking forward.
Good afternoon, everyone. First of all, I would like to thank the organizers and Anand for inviting me for this talk. I'm really grateful for this opportunity, and it feels really good to be here. So today I will talk about phonons with angular momentum, about their magnetic properties and applications. So first I will try to describe angular momentum of phonons, then I will talk about something called chiral phonons and how they respond to different physical stimuli. And then I will talk about magnetic moment of chiral phonons, and then the mechanism for this phonon chirality and magnetic moment. Then I will present a microscopic model for orbital-lattice coupling, like how this magnetic moment arises from orbital-lattice coupling in certain cases. Then we will talk about different materials where this kind of orbital-lattice coupling mechanism can manifest. Very briefly, I will also touch on group theoretical aspects of chiral phonons, which would provide us some insight about what kind of materials these phonons can occur in, and then what applications. So to start with, what is angular momentum? I'm not going to give you a definition, but you all know, well, we have an answer in this book. So I would say, for me, what is angular momentum? It's the second most important topic in this book. And it's the most difficult topic, I think so. I think the most important topic is harmonic oscillator. Well, we know that angular momentum is very important for electrons and nuclei, and different kind of coupling between different kind of angular momentum is at the heart of many exotic phenomena in physics, whether it's hyperfine splitting, or magnetism in materials. But angular momentum is also important for photons. So we know that photons can carry something called spin angular momentum, which arises from the circular motion of polarization vectors. So if we look at the cross section of this beam, and if you have like a circularly polarized beam, then the polarization vector moves in a closed loop, and that gives it spin angular momentum, depending on whether it's rotating in left circular manner or right circular manner. And if you look at this cross section, that at any 2 points, if you assume that the beam is coherent enough, then this polarization vector is moving in the phase. Like both of them are moving in phase. On the other hand, it was realized like about 30 years ago that angular momentum can also arise from the spatial distribution of fields. So if I take a cross section of beam and I look at two different points on this cross section, you can have a situation where the polarization vector is pointing in the same direction, but there is a phase difference. And that gives rise to orbital angular momentum of photons. Similarly, it's proposed that phonons can also have angular momentum. For example, you can have circular motion of ions, which can give rise to something similar to a spin angular momentum. Or you can have a situation where the lattice displacement at neighboring atoms has some phase difference. It's not exactly similar to OAM beams because we have a discrete lattice here. We have some rotational symmetries which kind of restricts the values of L that are allowed in this case. For example, if you have like some C n-fold symmetry, like n-fold rotation, then you can have angular momentum 0, 1, 2, n minus 1. Sorry, there's a typo there. So what is the angular momentum of this, what is the angular momentum of phonon? If I take one phonon which describes the circular polarized lattice vibration, like the quantized form of that circularly polarized lattice vibration, what is the phonon angular momentum associated with it? Let's first consider this classical picture where we have this phonon displacement, which is described by this U and U2. These are like the atoms in your unit cell, and I'm going to focus only on zone-centered phonons. So we can talk only in terms of unit cells. let's say we have some normal coordinate q, which we can write as q sine omega t, cosine omega t, x and y direction. So this lattice vibration would have an angular momentum omega q square. Now, assuming classical harmonic vibration energy per unit cell, omega square q square, then we can get number of phonons, and we can show that this angular momentum is h bar times n photon. So we can say like one quanta associated with the circularly polarized lattice vibration has an angular momentum of 1 h bar. Similarly, we can also use this quantum picture where we express these normal coordinates in terms of creation and annihilation operators, and the same thing for velocity. And then also we can write down the circularly polarized phonon as superposition of x and y motions, and then we can show that this angular momentum should be plus minus h bar. So now I have showed like this should carry an angular momentum plus minus h bar. So how do I get these phonons? So
one second, please. So this omega comes out of the natural material characteristics
right.
at the moment.
Right. So it's the frequency of the phonon that we're considering. And also like I'm taking only zone-centered phonons, and for now I'm focusing only on optical phonons. I think I should do so. So it would be like something in the range of like 10 to 100 MeV. So now you can get this kind of motion by getting the superposition of like x and y phonons, like horizontal and vertical motion phonons, for example. But in most cases, these two superpositions will have the same energy. But in some cases, you can get a scenario where the two phonons, left circularly polarized and right circularly polarized phonon, they get different energies. Like there's a splitting of these phonons, and such phonons are known as chiral phonons. When the energies associated with right circularly polarized and left circularly polarized phonons are different. So these phonons are obtained from like degenerate, doubly degenerate phonons, and then like there can be some internal mechanism which can lead to this. So actually this kind of phonons can also occur at some high symmetry points if you break inversion symmetry, or they can break at the center of your Wigner-John if you break time velocities. Recently there has been a lot of interest in studying this kind of phonons. For example, these works, both of these works have, so the first one is the theory work where they discuss the angular momentum of very chiral phonons. So you have a honeycomb lattice, and you have some very chiral phonons. So these are the phonons which come with some finite momentum at high symmetry points, and they can carry angular momentum. And that can be different at two, and that would be different at two values. Similarly, in this science work, it has been demonstrated, this kind of phonons have been demonstrated experimentally, where they assist some excitations which are otherwise not allowed. So what makes these phonons interesting is how they respond to different chiral quantities. For example, they couple to circularly polarized light. In some materials, they show circular dichroism. They show like different absorption for right and left circularly polarized light. In some cases, they show halicity changing Raman scattering. So you send a right circularly polarized photon, and then you get a left circularly polarized photon. Basically, there's an exchange of angular momentum. For me, the most interesting part is their magnetic behavior. So they couple with magnetic field, and this coupling is chirality dependent, and they can also exhibit Z-band effect. Another related process is phono-magnetic processes. So what happens, like once you excite this kind of phonon, in certain cases they can generate a very large effective magnetic field. In this paper, it was shown that you can generate a magnetic field as large as 50 Tesla by exciting such phonons, which is very high. And you can also get like some other analogs of EM processes. You can get inverse parity analogs, for example. So today I'm going to focus on magneto-phononic processes. I would discuss how strong is this coupling and what is the mechanism behind this coupling. So first of all, why should these circularly polarized phonons couple to magnetic field? Let's consider a simple classical scenario. So I have some ionic solid where we have different ions with different charges, and they are moving in circular motion. So if they are moving in circular motion, then you would expect them to, like they have some angular momentum, but they will also have some magnetic moment. And now we can calculate the magnetic moment of this full phonon by including like different ions, And then from there we can say that this angular momentum would be of the order of nuclear magneton. In fact, somewhat smaller. But if you choose your system carefully, you can get some magnetic moment as high as 7 nuclear magneton. And nuclear magneton is like 2,000 times smaller than Bohr magneton. So now if we look at phonons as a matter of fact, then you would get a very big splitting. For example, even at 50 Tesla with 7 nuclear magneton, you will get a splitting of only 0.02 centimeter inverse, which is 0.002 milli-electron volt. So on the basis of the simple classical picture, we should expect that the phonon G factor would be much smaller, would be smaller than 0.001. On the other hand, there are some experimental works. So these are some very old experimental works from the 1970s, and these are on rare earth paramagnets, where you have this Cerium 3 positive ion, which has 1 electron in 4f orbital. And this material shows this kind of splitting for some EG modes with a magnetic moment of the order of like 7 Bohr magnetons. And similarly, there are like a lot of materials in this class which show similar magnetic moments of the order of Bohr magneton. In fact, most recently, there has been some works on some topological materials where similar kind of magnetic moment has been observed for phonons. For example, in this work on lead tin telluride, which is a topological crystal insulator once you have enough doping with tin, then we see that as you change, sorry, the x-axis is missing, but it's supposed to be the doping x, and that line shows the transition, like the topological and non-trivial. So trivial and non-trivial. So in this material, like once you go into this topological phase, you get some phonons which have a magnetic moment again of the order of Bohr magneton. And similarly, this another material which is a dark semi-metal, you can see this splitting of left hand and right hand phonons again with magnetic moment of Bohr magneton. So this raises the question, where is this magnetic moment coming from? If we expect that on the basis of the simple classical picture, we should get some magnetic moment of the order of nuclear magneton, but what we are seeing experimentally, it's much higher. So where is this magnetic moment coming from? Well, it's of the order of Bohr magneton, so it kind of indicates that there is some contribution from electron spin. Somehow electrons are contributing to this magnetic moment. And in fact, many different mechanisms have been identified to account for this very large magnetic moment of phonons. So in first case, this magnetic moment comes from electronic band topology, which can be explained within the Bohr-Oppenheimer approximation. So you have a phonon, you excite some lattice vibrations, and then your electronic system follows it adiabatically. If your electronic bands have some non-trivial topology, they accumulate some orbital magnetization, and that contributes to phono-magnetic movement. And for those paramagnets that I'm showing you, in that case, it arises from coupling with electronic excitations, which I will discuss later. And similarly, for this dark semi-metal, it arises from the coupling with cyclotron resonances. So you have a dark dispersion. Once you apply magnetic field, you get these Landau labels, and now phonons can couple to the excitations between different Landau labels. Today, I'm going to focus on this electronic excitation mechanism, and it's a non-adiabatic process, like Bohr-Oppenheimer approximation brings down. So this mechanism operates in these rare earth paramagnets, where phonons coupled to crystal active field is split 4f states. We asked whether this mechanism can also occur in some other materials. For example, can it occur in some d orbital magnets, and can it occur in some other magnets where you have like some kind of super exchange interactions? And is it possible to estimate value of this orbital lattice coupling, estimate the value of this phono-magnetic moment from a microscopic model? So those works had provided a model, but they did not provide a microscopic model to estimate those values. So first I will describe the model which accounts for this phono-magnetic moment arising from orbital lattice coupling. So it's a generalization of work. So it's a generalization of this work, where this work provided a theory for these 4f rare earth paramagnets, but they did not provide a microscopic model. So here are like some minimal ingredients of this model. So we have our ground state, which is doubly degenerate, and these two states are time reversing partners. So we have a Kramer doublet, and these states they have some fixed angular momentum, J alpha, and magnetic quantum number Mj minus Mj. And then we have some other states at a slightly higher energy, which we call psi 3, psi 4. They are also Kramer doublets, but with very different angular momentum configuration. Basically, if you have to go from state 1 to state 3, that would include some angular momentum exchange. And now you can have phonons. So these are the two phonons that I have shown for, so these are like the two components of a doubly degenerate phonon modes. You can think of them as X motion and Y motion, for example. So now we have this electron-phonon interaction where these phonons couple these different states. So basically what these phonons are doing, these phonons are coupling psi 1 to psi 3, psi 2 to psi 4 in this complicated manner, and the form of this interaction is determined by time reversal symmetry. So these interactions can be explained, can be represented by these vertices, and then we can calculate like what they do to phonon energies by using Green's function formalism. So this is a non-interacting case where this is the Green's function matrix for two modes. So we have two modes, that's why like we have two components, and if you have to like find the frequencies of these phonons, you can just look at the denominator and equate it to 0. That's a very simplistic. Now we include the first corrections from these interaction vertices, and that modifies the Green's function matrix, and it introduces the self-energy terms. So we have this off-diagonal term, which is most important for us. So this off-diagonal term, basically it splits up the two phonons. So you can think of this thing as a 2 by 2 matrix where it was identity earlier, now you have like some sigma x, sigma y kind of terms. And also I will show later that these coupling constants have this term. Now once we get these phonons, these functions, then we can get phonon energies by solving this equation, which can be done analytically. And then to the first order in magnetic field, we get this equation. So this magnetic field enters into picture because this term is non-zero if you have delta 1 not equal to delta 2. So delta 1 and delta 2 were excitations into the states that I showed earlier. So delta 2 was for the time reversal partner. Or if the population of the two levels in the ground state manifold is different. You can think of them as up and down spin. So by applying magnetic field, you can change their population. In order to get these terms non-zero, we'll have to break time reversal symmetry, which we do by applying magnetic field. And this, we see that it has two contributions. One arises from the energy differences in two cases, and another arises from the population difference of two states within the lower energy manifold. And this term is directly proportional to magnetization of the system. For a paramagnet, it will have like a 10 hyperbolic term. It will also have a temperature dependence. If you want to consider a simple picture, so you can also think like if you have this sigma y kind of term, the new phonon modes also get modified. Earlier you had x and y, which were your eigenstates, and the system was degenerate. But once you include those interactions, you get these new phonon modes, and they are this kind of superposition which are chiral. Now, if we want to consider, we can actually visualize this whole interaction in a very simple way. Let's say if this condition is satisfied, then you can write it down in terms of this left circularly polarized phonon displacement and right circularly polarized phonon displacement. So what I have this excitation, electronic excitation on the magnetic ion, which involves a change of angular momentum by 1, let's say. And then we have a phonon which also carries an angular momentum 1. So now these two excitations would hybridize. It's very much similar to what you see for exciton-polariton coupling, exciton-phonon coupling, and you get those polarities. So this phonon, this right circularly polarized phonon couples to this excitation, and the opposite phonon, which is time reversal copy of this phonon, it couples with another excitation, which is the time reversal copy of that excitation. Both of them hybridize, and that changes the frequencies of these phonons. Well, it changes the frequencies, but they still remain the same if time reversal symmetry is preserved. You can also visualize this process like this, where I have two energy levels for phonons and two energy levels for electronic excitations, and they hybridize. And as you can see now, we have two phonons whose energies are different, but they are still degenerate. But once you apply magnetic field, then this degeneracy is lifted for two reasons. One, that excitations that I showed you, this delta 1 and delta 2, their energies become different. Second, the population for excitation 1 and excitation 2, they also become different. So as a result of this degeneracy of two phonons is lifted, and it's lifted in a way that the new eigenmodes are right circularly polarized and left circularly polarized vibrations. And this splitting is non-zero only if delta 1 minus delta 2 is 0 or f1 minus f2 is 0, which I mentioned earlier. Now this splitting depends on a lot of factors. First thing which we need for this splitting is that these deltas need to be closer in energy to phonons. And that's a very difficult thing to do. Like that's very material specific thing, because phonons depend on material, like their frequencies depend on materials, and similarly these electronic excitations also depend on the magnetic ion. And another thing that we need is the electronic G factor of the states, because how much they would be shifted, how much their populations would change with applied magnetic field would depend on this gamma. And of course temperature, because that would decide the population imbalance between two quantities. So there's one more factor. So all of these things we can measure, but there's one more factor, that is electron-phonon coupling. So phonon has to couple to these excitations somehow. So here I'm considering an orbital-lattice coupling mechanism. So what is happening, like you have a magnetic material, you have a magnetic ion which is surrounded by some ligands, some, for example, some oxygen ions or chlorine ions. And once you excite a phonon, which reduces the symmetry of the system, it changes the crystal electric field around that magnetic ion, and that introduces some perturbation to that crystal electric field. And now you can expand this crystal electric field in terms of these states of that magnetic ion, and then you can find these coupling constants. And this is the approach we use, because like these states that I talked about, I said that they were characterized by some J and Mj, and this Mj is coming from orbital and this spin degree of freedom. Now if you perturb this crystal electric field around this ion, that can couple different states in this magnetic ion. So first we apply this to this well-established case of rare earth trihalides, which was studied in 1970s. So this is a rare earth trihalide, cerium trichloride, where we have this cerium 3 positive ion, which is surrounded by 9 chlorine ions. And this is a 4f orbital system, which means the spin orbit coupling is very strong for this material. So if I take like one electron in 4f system, if it's a free ion, then you have all of your f orbitals have the same energy. But once you have some spin orbit coupling, which is very strong for these materials, as you keep on moving down in periodic table, the spin orbit coupling keeps on increasing. So this material has spin orbit coupling of the order of 100 MeV. And f electrons are very well shielded, so they don't feel the crystal electric fields effects that much, but they still feel some effect from crystal electric fields. In this case, you get these this distribution once you consider the effects of crystal electric field as perturbation. So the point to note it here is that we have these electronic labels for these low energy labels on this material, which are characterized by J, pi by 2, and Mg to different values. So they are all coming from the same J multiplier. And next we consider some EG phonons. So we can obtain the displacement for these phonons from group theory. And then we find out like how they change this crystal field around the Cerium 3 positive ion, and then we write it down in terms of these X and Y and Z. So in terms of like position coordinates around that Cerium nucleus. And what it does, it basically introduces coupling between these different states. For example, when you write these terms X, Z, Y, Z in terms of these states for J and Mj, you can see that they are coupling like different states. So in this case, this particular phonon is coupling plus minus pi by 2 by plus minus 3 by 2, which is about 14 MeV. And this phonon has energy 23 MeV. So the scales are matching, which is good enough. Usually that doesn't happen because the phonons are at like 50 MeV and these excitations can be very small. And then we apply this model and study like how this splitting of these phonons changes with magnetic field. and this is what we get. We basically see a splitting of about, we see the saturation splitting of about 1.2 MeV, and this saturation is coming from this 10 hyperbolic factor because we had this low energy manifold with up and down spin, and we applied some magnetic field. And you can see that it compares quite well with these results from 1970s, where their saturation splitting was 18 centimeter inverse, and it was saturating around 2 or 3 Tesla. So we should be looking at this 200, this phonon at 200 centimeter inverse. And by applying that model, then we can show that we get a chiral phonon in this case, which is characterized by this kind of motion where these chlorine ions are moving out of xy plane, like they are moving along z direction, but there is a relative phase between different ions. Similarly, we can now apply this model to other phonons, and we see that there is another phonon E to G which couples these plus minus 5 by 2 and plus minus 1 by 2, and similarly this other phonon. And in this case, the combination like this chiral superposition gives rise to the circular motion. So what we see is that there is a considerable splitting of phonons, which indicates that these phonons can carry a magnetic moment of the order of Bohr magneton. In this case, at 10 Kelvin, this first phonon shows a magnetic moment of 3 Bohr magnetons, which at least by order of magnitude wise, it's very, it's in good agreement with the experimental results. I mean, this is a very crude model, so I think we can't expect a very, very good agreement, but I think it's good enough. Now, next question we ask, like having tested this model for their paramagnets, can we apply this kind of physics in d-electron systems? So let's first very briefly review what is different for d-electron system. So the f-electron system that I was showing you, it had like a very strong spin-orbit coupling, and then crystal electric field excitation was the splitting of these levels. But on the other hand, for d-electron systems, we know that crystal electric field excitations are crystal electric field energies are very high. So we see this splitting of d orbitals in T to GPG, which is of the order of 1 eV. So this is not compatible with optical phonons because they are usually lower than 100 MeV. However, there are mechanisms through which these T to G can split further. For example, spin-orbit coupling or some other mechanisms. For example, you can have some trigonal distortion in your system that can also split up these levels further. In fact, recently, there is a group at UT Austin, Professor Elaine Lee's group, who have detected a very high magnetic moment for some EG phonons in quantum magnet Cobalt type 8. So in this case, Cobalt 3 positive, sorry, it's Cobalt 2 positive, it has 7 electrons in its outermost shell. And they have noticed the phono-magnetic moment of the order of Bohr magneton again, and to the best of our knowledge, this is the first such example in a d-orbital quantum magnet. So now we would apply our model to this material, but before that, I would very briefly talk about like how we measure this magnetic moment. So this magnetic moment is measured by through this helicity resolved magneto-Raman spectroscopy. So you have this cross-circular channel where you send in a right circularly polarized phonon and you observe oppositely circularly polarized phonon. And then what they notice is that this peak for this phonon, it splits up as you apply magnetic field in a certain direction. And that happens only if you apply magnetic field in z direction, which is like the z axis in this case and not in y. I will talk about that too, like why this one direction is important. And then it indicates that this exchange of angular momentum which is happening, it's basically going to this excitation, this phonon excitation. So here again, we are proposing that in this case, this mechanism is arising from this orbital-lattice coupling. So in order to understand that, let's first look at what is the structure of this material, what are the characteristics. So in this material, this Cobalt 2 positive ion sits in this octahedral cage of oxygen ions, which is slightly distorted, like it's trigonally distorted, which means that the symmetry, side symmetry is reduced to 3-fold rotation. And there is a considerable spin-orbit coupling, so we cannot like treat any of them as perturbations. But what we see, like once we take into account this spin-orbit coupling and trigonal distortion, and this kind of things happening still, like this electronic energy diagram has been shown in this paper. So we are going to focus on these two low-lying energy states, which can be characterized by mg plus minus 1 by 2 and mg plus minus 3 by 2. I mean, technically they cannot be characterized by a fixed j, but predominantly this lower manifold is j half and the upper one is 3 by 2. And we are not going to worry about other states. So now what happens, now we have these EV phonons here, which have energies around 20 MeV, so 26 MeV, 23 MeV, and this excitation has energy 23 MeV, which is again putting it in close proximity. Like these two energies are in close proximity, so it's highly visible that this kind of effect might occur here. But this material is very different than what I was talking about earlier, because that was a 4f system. I had only one electron and it was a paramagnet. So there was no magnetic phase transition. However, in this material there are two differences. First is that these two states, these two energy manifolds that are important for my model, they are coming from different J values. And second, there is a magnetic phase transition. So once you go below 38 Kelvin, what happens is you get this antiferromagnetic ordering with opposite, with antiferromagnetic ordering between two planes and ferromagnetic ordering within two. Which means that from exchange interactions, you will get some magnetic field. Even if you are not applying any external magnetic field, you will get some in-plane magnetic field. But this is an in-plane magnetic field, so it hybridizes, so it opens up a gap in these two states that I was showing you earlier, these two states, and it hybridizes them in a way that the angular momentum along z direction comes out to be zero. But the phonon carries angular momentum only along z direction in this case. But once you start applying magnetic field, you can change the eigenstates of these states such that they gain some angular momentum, which makes this process, which makes this mechanism feasible again. However, the temperature dependence would be very different. Earlier we had that tan hyperbolic kind of dependence, but here it would be very different depending on the magnetic susceptibility of the system. So first we calculate the splitting for t greater than Tn, which is the paramagnetic case, and here again we apply the same microscopic model, and then we find that magnetic moment is 0.1 and 0.24. But next we study temperature trends, and for temperature trends I am going to focus only on one of those phonons, that is 33 MeV. So then we include this in-plane magnetic field, and we take into account the eigenstates, like how these eigenstates are changing with this applied magnetic field. And this applied magnetic field is itself a function of temperature, because it depends on magnetic ordering. As you keep on going below, a new temperature keeps on increasing. So you can already see that there is some saturation in this phono-magnetic moment, which is indicative of this in-plane external magnetic field. And these are the experiment. These are the values measured from experiment. So our theory matches well for order of magnitude, like we see 0.15 Bohr magneton, and the trend is very similar. However, it doesn't agree very well with the magneton. It could be because like our model is too crude. This microscopic model for electron-phonon coupling is not giving us the right orbital-lattice coupling. So we tried to do a best fit by changing this orbital-lattice coupling, and we found a reasonably good fit if we use a value which is twice the value that we obtained from our microscopic model. So, so this orbital-lattice coupling model can also be applied to some d-electron systems. That's one of our main conclusions. Now, very briefly, you might ask, like, where else should I look for this kind of phonons? I think group theory can provide us some insight. So what was common in these two different materials was like we had some doubly degenerate phonons, which are represented by these irreducible representations, e.g. EU. And then your time reversal breaking, then once you break time reversal symmetry, these irreducible representations should break into two one-dimensional terms. We don't have to go into the details of all those terms, but you can think of this thing like that. So you have, let's say, px and py orbitals, let's ignore pz for one moment, and you apply some magnetic field, you break time reversal symmetry. So your new eigenstates become px plus ipy and px minus ipy. So the same thing can be reflected in these irreducible representations, which you can read from character tables. And now the symmetries of your system should be such that they should allow an exit vector, because the angular momentum that we are looking at is an exit vector. So if we look at the character tables, then an axial vector, like the z component of this axial vector, should occur in this trivial irrev, which means that it should not be affected by any component of your symmetry. Like if you do any of those symmetry operations, you should still get the same axial vector. For example, that is the case for C3 and for C3H, where you have a plane where your mirror plane is perpendicular to your rotation axis. Sorry, I think I'm mixing the two. So in C3H case, your mirror plane, your basically your rotation axis lies in your mirror plane, so it doesn't change the axial vector. But in the other case, it does change the eigenvector if it's perpendicular to the rotation axis. And on the basis of this kind of symmetry analysis, we made this list of magnetic point groups. So this information about irreducible representations can be obtained from, I forgot to put the reference, but from Bilbao crystallographic server. And we found these magnetic point groups which can allow for this kind of Jones-centered chiral phonons. And in fact, this example of cobalt titanate that I was discussing, it falls in this category. For example, you can also have a situation like this. Let's say you have some C3 symmetry, which allows this kind of axial vector. Then you also have, let's say, some two-fold rotation, which maps it to negative of itself. So you cannot get an angular momentum in this case. So you cannot get a chiral phonon in this case. However, if you have a setup where C2 is broken, but C2 times time is preserved, then you can have this axial vector. This axial vector is allowed by symmetry. That's, for example, the case for this magnetic point group. Now, what are some other situations where this kind of orbital lattice coupling mechanism can arise? So, for example, I think this mechanism can also arise in 4D magnets, and ruthenium trichloride might be a good candidate. It has reasonable spin-orbit coupling. So, spin-orbit coupling is usually higher for 4D and 5D in comparison to 3D. It also has trigonal distortion. So, it does have these EG modes, and it has some low energy excitations which are at about 100 MeV and some optical phonons which are at about 50 MeV. I mean, the scales are not matching very well, so the effect would be somewhat weaker, but I think it should still be stronger than nuclear magnetic phonons. So we haven't done that calculation yet. And another question we can ask, like right now is breaking time reversal symmetry by applying magnetic field, but what about if you have a ferromagnet where the magnetic order is such that you get some magnetic field Z direction? That would also break time reversal symmetry in a manner that will also break time reversal symmetry in a manner that it leads to this phonon-Zeeman effect. I don't know any such examples at this point, but there's this paper for gold chromium triiodide where they have this kind of ferromagnetic setup, but they explain this magnetic moment on the basis of coupling with magnons. Another scenario you can imagine is Floch engineering. So you apply a circularly polarized light that breaks time reversal symmetry of your system, and that gives you chiral phonons. For example, that can occur in graphene. So circularly polarized driven graphene, circularly polarized light driven graphene is very well studied both theoretically and experimentally, and it's known that you can get topological bands in the system by applying a circularly polarized light. So we can ask like what would happen like if you couple phonons to these Floch bands, these new bands which have some finite band curvature. And this is one direction which I am pursuing with Professor Takashi Oka from University of Tokyo and my postdoc advisor Greg Field. So having talked about all these mechanisms, now let me very briefly talk about applications. So we have these chiral phonons where we have this kind of circular vibrations. Now what to do with them? They also respond very strongly to magnetic field. So first thing that we can do with them, so I think I put that reference earlier, is that they can generate a very large effective magnetic field. I think the microscopic model that I applied for phono-magnetic moment would also explain this giant effective magnetic field. In those papers, it was described on a very phenomenological basis, like they had used a very different analysis. So one thing, like if you can generate this kind of giant effective magnetic field by applying an external laser, it means that you can basically control the magnetization on an ultra-fast time scale, which is very important for electronics. So you can control the magnetization of your system at ultra-fast time scales, and that can have some major implications for information processing. And as I mentioned earlier in that paper, it was shown that you can achieve very high magnetic fields, which can help you to study phase transitions at very high magnetic field in some materials. And then you can also use that effective magnetic field to control the magnetic order on ultrafast time scale. Similarly, another aspect of these chiral phonons is, in some cases, they are also connected to non-trivial phonon band topology. That is one thing, and they can also exhibit this thermal Hall effect. I think there are two contributions. In this case, one comes from the non-trivial topology of these phonons, and one from these chiral properties based on phonon angular momentum. So now you can have much more efficient thermal transport with these chiral phonons. And this kind of chiral phonon based thermal transport has been shown in QuIC in this paper. Another implication that you can have is in 2D optoelectronics. So you can have chiral phonon assisted transitions. There are certain transitions in some materials which are forbidden due to angular momentum conservation. Like you have like much higher angular momentum, you need much higher angular momentum for those transitions. But if you can like have some chiral phonon assisted transition where some angular momentum is provided by the chiral phonon, then those transitions can be allowed. Or it can have some important implications for exciton phonon coupling as well. So I discussed like the energies, like how this phonon-Zeeman effect manifests, but there is also another aspect of these chiral phonons. That is their scattering processes. So how do they scatter? Because they carry angular momentum, so their scattering would be much more restricted, which makes them very long-lived, and it can have some very interesting consequences for spin relaxation and scattering. Another thing that this model can do in our case, like if we apply this model and we study some chiral phonons and they're splitting in magnetic field, that can also serve as a probe for orbital lattice coupling, or in some cases a probe for electronic band topology. With this, I would like to conclude. I think I still have time, but so I provided a microscopic model for phono-magnetic moment, which was based on orbital lattice coupling. And then we provided some estimates of magnetic moments in different classes of materials, and we also predict some new materials where this kind of effects can occur, and some new mechanisms, for example, this Froke engineered thing. However, there are a lot of aspects of these chiral phonons which haven't been studied yet because this area is very new. For example, the model that I had considered was a molecular model. So I just looked at the unit cell and I treated that whole system as a molecule. But now you can also have like itinerant bands, like you have these bands in your system, and you might ask like how do electrons couple to those magnetic ions, which are those magnetic degrees of freedom which are moving around. Similarly, they can also couple to some other excitations in the system like magnons. And I looked at only at the zone-centered phonons, but what about finite K phonons? Like would they have similar Zeeman effect? And another possible applications would be like what happens to like phonon line widths. Do we see any changes in phonon line widths with magnetic field? And because we believe that angular momentum conservation should restrict the scattering and that it should narrow the line widths, but this is something we haven't studied yet. And it would also provide, if it changes, like if we can control it with magnetic field, then it will also provide us a mechanism to tune scattering rates by applying some external magnetic field. With this, I would like to thank my collaborators, my advisor Gregory Feet from Northeastern University, Boston, and my other collaborators from UT Austin, Tel Aviv, and University of Tokyo. Thank you for your attention.
Thank you, Swati, for that nice talk. So, questions? Hey, you can all here. Do you have a question? You don't have a question? Okay, sorry. Other question?
I think
Just a little, that's all. You just have to be a little louder. Okay, so actually, the system, is there any timing inversion symmetry in the system or no? Of this kind of
so. In this case, there was no inversion symmetry. There was only time inversion symmetry for the examples that I discussed. But you can have a situation where you don't, like where you have inversion symmetry broken. Oh, sorry, there was inversion symmetry in these systems. Inversion symmetry was not broken, but you can have a setup where inversion symmetry is broken. In that case, you will get chiral phonons, but you will get it at some high symmetry points. So basically, you will get chiral phonon at one K point, and you will get a chiral phonon at another K point, but their chirality would be opposite. Like for the overall billion zone, overall chirality would be 0. But you can have, like at a particular momentum, you can have some chiral phonon with that finite chirality. And that's the case for graphene emission.
So you have strong electron phonon coupling in your system. So how would that affect the electrical conductivity if suppose your the angular momentum of these phonons is very high? Would it sort of, I mean, I would think that maybe the conductivity would be strongly affected.
Right. The scattering mechanism
Yes.
would be kind of suppressed, like if you have these.
So how would that get affected?
So I think first thing is that would depend a lot on the material. So if you can like design your system in a way that now your phonon modes are chiral, like if you let's say apply some external magnetic field or some other time symmetry breaking mechanism, then I believe that would increase electrical conductivity, because that would decrease the scattering events, and that should increase electronic conductivity. But that would,
naively, I would think that it would make it more robust against scattering. So, but how much would it increase?
Yeah, so that so for the scattering part that I haven't done.
In topological insulators, you have this spin moment.
Right.
Which
So
actually prevents
it's
scattering
by
to
a very large extent. So I don't have much idea about, like, I haven't quantified that thing, but I think there should be a considerable effect. In fact, in that QuIC paper that I was showing, so for electrical and thermal conductivity, you have this Weidmann-Franz law. So they showed that it's violated very strongly in QuIC, and they have attributed that effect to chiral phonons. I mean, they have experimental results, but theory-wise, in that paper, they haven't quantified it. So I don't think there is a mechanism, like there is any work at this point which has considered this kind of.
Okay, and another question is that your data was showing that your this chiral moment, these chiral phonons have a large magnetic moment.
Right.
So, and your model is that it is sort of coming because of the hybridization with the electronic states.
Right.
So, is it possible that one is measuring a part of the electronic magnetic moment itself rather than
Yes.
the orbital part of the moment rather than actually the
phonon part? Right. That's a very good question. Yeah, actually, that's what I think what's going on, because what you are seeing is not a pure phonon, but it's an admixture. But the thing is, like, that admixture would be very small, like the electronic excitation percentage would be very small. In fact, in some of my other, like, I haven't presented those results, but we had tried to quantify it, and it was about 10%, I think, for this EG2 phonon. Like, the mixing was about 10%, because it's slightly far from resonance, so it's not like the hybridization is not very strong, but there is definitely a very small, like, there's definitely this part from electronic excitation. And now electronic excitation has some Bohr magneton, like magnetic moment of Bohr magneton. So it's possible that this 0.1 Bohr magneton that you're seeing is coming from that electronic excitation. And
so it's some sort of like a composite state that you're measuring.
Right.
Like the electronic and the phononic states together, which are contributing to that.
Right, but that part of that electronic state is very tiny, because we are quite far away from this level crossing point.
The temperature should determine the difference between the two, right? I mean, the phonon part should probably die out, or
No, but actually the energies are very close. 23 millielectron volts and the this thing are very close to each other. So those states come very close to the phononic. So they perhaps have a similar temperature difference or whatever. I don't know.
Also, like, even for the electronic excitations, like, their energy also move with magnetic field. So the hybridization amount also changes as you apply magnetic field. Yeah, but that's I think.
But since you have hybridized it, so then you don't know. I mean,
If you can call it phonon or not,
Yeah.
that's the question. But I think as long as it's very small, it's okay to call it phonon.
but you need a model that couples.
Yeah, but like whatever phononic part you will get, like it will have like some circular motion associated with it. So I think it's okay if you want to call it chiral phonon.
So just tied to that question, so how do you measure the splitting Raman spectrum?
Yeah, we measure it in Raman spectrum.
No, so and line widths, how do they measure? If at all of the circular kind only?
I
I'm
think
a little
they
concerned.
did. I am not very familiar with this line width measurement. I think they did that. So we are still working out the theory for this line width actually.
Okay.
Yeah, I think they just, I mean experimentally they just measure it from here, like the full width, half maximum.
No, that's
Yeah, sure.
okay.
Yeah, but we are still working
No,
out
I-
the theory for it.
I'm not a charismatic person. So how does one actually measure phonon line widths? Even let's say optical novel stuff. I don't know.
One is definitely Raman experiments, like you can do that.
Okay.
And
Now I want to see the distinction, if any,
like
between
from
the
magnetic
normal,
excitation.
for the one which are twisted. Let me put it that way.
Right. Also, I think their temperature dependence is very different
Very
for
different.
phonons because I'm forgetting the name of that thing, but you have this enharmonic decay. Like if you take an optical phonon, it decays into two acoustic phonons, and then you get a very peculiar structure from there for line width, and you do that fitting to temperature, and then you can say that it's a phonon. And in some cases, there can also be like some asymmetry, but I think it's not. It's more related to like electron-phonon coupling. Like you can have this Fano shape kind of thing.
Okay.
That can also be there. And then I think that then you can distinguish like contributions from electronic excitation. Yeah, but in this case, I think it's a good question. Like if you can somehow separate the two contributions experimentally, like what is the phononic part and what is the electronic excitation part.
Other question? Okay, if not, let's thanks Swati again.